Hi everyone, welcome back to our channel. Today we are going to learn some few basics on Norton's theorem. So what is the statement of Norton's theorem is? So any two terminal. So two terminal means it is a resistive network. This is terminal 1, this is terminal 2. Any two terminal linear. Linear means resistive element, inductive element and capacitive element, and bilateral. Bilateral means it has to allow the current in forward direction and it has to allow the direction in reverse direction also. Okay, any two terminal linear bilateral network, big network is there, it can be replaced with an current source. So this is nothing but the current source of a magnitude Is, and with an internal resistance where this is called R Norton resistance is called, can be represented by an Norton's equivalent circuit like this. So here the theme is a network will be given and we need to find out the load current I. The load current I can be found as by drawing Norton's equivalent circuit is. So first take the given circuit and find the short circuit the load resistance and find the current ISC and find out R Nortons also. Okay, the formula for IL is, I'm going to apply current division rule. What is the total current? ISC. Okay, ISC into, in this branch I require current. What is the opposite branch? Which is nothing but R Norton divided by the sum of resistors which are connected in parallel, which is nothing but Rn plus RL, what is given in the problem. This is how we can find out the load current or the current in any branch using Norton's theorem. Okay, I repeat the theorem. The statement of Norton's theorem is any two terminal means it is nothing but resistor consisting of two terminal, any two terminal linear. This element should be an RLC, resistor, inductor, capacitor, bilateral. They have to allow the current in uh, forward direction as well as in reverse direction, can be replaced with an equivalent source consisting of a current source in parallel to an shunt resistor. And this theorem is dual to that of the Thevenin's theorem. Okay, it is reverse, or the dual of this Norton's theorem is nothing but Thevenin's theorem. Okay, so we have the reverse what we done there, and the procedure of finding R internal or R Nortons is same procedure as that of Thevenin's theorem. Whatever the, if you want to check out, if you want to know about the basics of the Thevenin's theorem, you can check out in the previous page. The procedure of finding R Nortons when you have independent source, the procedure of finding R Thevenin is same. So there are three ways of finding resistance. If you have independent sources, how to find R Nortons or R internal. Okay, so second one is when you have dependent source as well as independent source. So we have the formula of R Norton is equal to, first we want to find out VOC and then we have to find out ISC, we can find out R Norton. So third procedure is when we have only dependent types of sources. Okay, so like these dependent types of sources, then we can find out Norton's equivalent is apply a DC excitation of VDC and find the total current drawn by the network, then we can find out R Nortons. And here also the same procedure, first find the open circuit voltage and short the load and find out ISC, then you can find out Nortons resistance. So the procedure of finding R Nortons or R internal or R Thevenin is same that of the Thevenin's theorem. Okay, so here I can say that Thevenin's theorem and Norton's theorem are basically, so if you understand Thevenin's theorem, then automatically you can understand the both theorems. Okay, so very simple here is, here we have an voltage source which is nothing but Thevenin's voltage source in series to a resistor. Okay, and this is the resistor. This we are going to call it as Thevenin's resistance and replace it with an load. Okay, so the load resistance may be given to you So just replace the load resistance RL. So here I am going to find the current directly by IL is equal to V Thevenin divided by R Thevenin plus RL. Okay, this is the one property of Thevenin's. Here R Thevenin and RL are connected in series connection. Okay, so R Thevenin and RL are connected in series. So the duality of Thevenin's theorem is once again Norton's theorem. Here you are going to have an source but not an voltage source. This is nothing but a current source ISC in shunt with a resistor, where this resistance is called Norton's resistance. And here we are going to have one more resistor where this is called as a RL. We need to find out the current in this branch. So how to find the current in this branch is already done. IL is equal to the total current. What is the total current of the network? I am using current division rule. So load current is equal to total current into, in this branch I want the current. What is the branch in parallel to this one? So into the parallel branch resistance divided by the sum of resistors which are connected in parallel, which is nothing but Norton's resistance and Norton's load. Okay, here you can see here from the observation. So basically these are dual in nature. So here Norton's resistance and load resistance are connected in parallel. This is the main difference. Here the Norton resistance and load resistance are connected in parallel. Okay, here the Thevenin's resistance and load resistance are connected in series. That's why I can say Thevenin's theorem dual network is Norton's theorem, or the duality of Norton's is Thevenin. So here we find voltage. So here we discuss about voltage, and here we discuss about current, where voltage and current are once again dual in nature, where series and parallel are once again dual in nature. Okay, so where Thevenin's theorem and Norton's theorem are once again dual in nature. But what you have to understand is, in both the networks, what we are finding is current. We are finding the current across any resistive branch. The procedure is same. So that's why if you understand Thevenin's theorem, just dual of the Thevenin's theorem is nothing but Norton's theorem. So these three way of finding Thevenin's resistance or Norton resistance, the procedure is same. I repeat it again. When you have only independent sources, so the procedure already you know that if you have an voltage source, just if it is some 10 volts, so deactivate this. Deactivating this means making that voltage as 0, which is nothing but V equal to 0. If you have an current source carrying a current of 10 amperes, so deactivate the current source. How to deactivate the current source is just make it open, therefore current becomes 0. So this is the procedure of finding Thevenin's resistance or Norton's resistance, and this circuit is called Norton's equivalent circuit, and this is called Thevenin's equivalent circuit. Both are dual in nature. Okay, so that is the important. The statement is almost all also the same. Any two-terminal linear bilateral network can be replaced with an voltage source and in series with an Norton resistance. Okay, so this is how to understand the theme of Norton's theorem or Thevenin's theorem is to find current across any branch. That resistor is nothing but load resistor. So this is the one of the procedure. Okay, you find the current by any of the method like nodal analysis, mesh analysis, super node, but the question itself you will specify find the current using Norton's theorem, then you should use this method of solving. Hope you are able to understand. Let's try to do one problem, then you'll get more confidence. Okay, if you solve more problem, then automatically you can understand what is the confusion in the problem. So by solving more problem, the confusion you can overcome and you can solve more problem. If you feel my content is useful to you, please like the video for the hard work what I'm making for you. Please share with your friends. If you have any doubts, let me know in comment section. And if you're watching the channel for the first time, subscribe to my channel KV Tulsi. And if you have any doubts, let me know in the comment section. Thank you for watching patiently. We'll meet in the next video. Yours Ram.